stars that have been discussed so far are slow rotators. Yeah? And we understand that pretty well, why that is, from looking at the outside. Yeah? But I'm going to be discussing other stars. Yeah? And here you actually see, even this stick doesn't make me tall enough. But anyway, you see actually the mass range indicated here of stars where we can apply astroseismology these days. So Jörn and Douglas has been here. Jörn has been sort of like this range here. We're going to go here now to very massive stars. And because they are massive, they live much faster, only a few million years instead of several billion years. And so since they are production factories of elements other than hydrogen and helium, well, these are the metal factories of the universe, as I tend to call them. And we've had several thousands of generations living their life, and they rotate very fast. From almost no rotation, where stars are spheres, as Douglas stressed so much, to almost a critical rotation. And what does that mean, critical rotation? It means that you go so fast that the centrifugal force overcomes gravity and the gas flies away, okay? And so we know that these big blue stars, my favorites, tend to rotate very fast. Now, why is that? Because stars like the Sun and lower masses, well, they have this nuclear production in the core, as Douglas showed it. Then the photons diffuse out the energy, and then it becomes a bit inefficient, so you have convective motions. Well, in these stars that I'm mostly focusing on, the energy production in the core is so fierce that they can't get their energy out efficiently enough by the photons. So they actually have this turbulent convection in the inner core and not in the outer envelope. So we flip around the structure of the star, basically, okay? And that's because these stars are actually not slowed down by a phenomenon that is called magnetic braking. So if you have a convection outer envelope, you create magnetism and you slow down the star because of angular momentum loss. But here there is no such outer convective layer. No, it sits in the middle. And so these tend to rotate fast because they don't have a way to get rid of their angular momentum. So that's why these stars tend to be fast rotators. Now here you see some, I'm a bit younger than my two colleague laureates, so a bit fancier, but I can't do these animations either. So again, Peter de Groot, who was already mentioned, is my guy who makes all these beautiful animations. So again, spherical harmonics, but this time for massive stars with turbulent convection in the inner side, and then rotation. Rotation is something that I cannot afford to ignore in my studies. As Douglas pointed out, like it's 1 in 1,000 the frequency shift due to the Coriolis force. Well, in my stars, the shift is as big as the frequency itself. And so you can't ignore that. Like 5-minute oscillations divided by 26 days, which is the rotation period of the Sun. 5 minutes divided by 26 days, that's a pretty small number. You can afford to ignore the Coriolis force in first instance. In big blue stars, you have these gravity modes, nicely introduced by Jörn. They have periodicities of about 1 or 2 days. And the rotation periods are also a few days. So a few days by a few days is 1. I can't ignore that, yeah? Because the frequency of rotation is as large as the frequency of the gravity modes in these stars, right? And so I don't have a Sun to learn the whole business of astroseismology from. I don't have a calibrator. And that's why it took us some time to set up astroseismology of massive stars. So here again the Sun, it has been discussed extensively, I won't go into it. 5-minute oscillations, acoustic modes in a slow rotator. And then you have the, as Jörn introduced it, you have the pressure force and gravity force that come into play, and that sets the mode cavities as we have just seen. But in my case, as said, I do have to care about the Coriolis force. Yeah? And if the star is magnetic, on top of that, I also have to care about the Lorentz force. I won't have time to go into that very much, I'm afraid. And, you know, as we will see later today, these massive stars not only tend to rotate fast, they also tend to have a companion that we can't ignore. And so we have to care about tidal forces. Again, I will have very little to almost no time. But that means that there's a force balance where there is more complication than what we've heard so far, okay? Are we scared of that? No, because we tend to love mathematics. And so here, let's simplify. You see a frequency axis. And what you've heard so far are fast waves in slow rotators. These tend to be spherical stars. Now we're going here. Slow waves in fast rotators. These are not really spherically symmetric, but that's something we have to deal with later on. But in any case, this is a beautiful equation. It's about the only one I have. That's the wave equation that we have to solve, where omega here is the angular frequency of the mode, and psi is the displacement of the up and down motion in these blue and red patches. Yeah? And as Douglas has stressed, it's quite small. So that allows us to linearize the pulsation equation. And so we basically have to solve a differential equation like this one. Doesn't really matter if you don't understand the details. But I have to care about this term here, which hasn't appeared in all the equations that Jörn discussed. That's the Coriolis force, right? And so it's just another term, right? It's not as simple as that, as Belgians would call it. But anyway, we try to deal with it. So how do we deal with it? Well, on the one hand, we have the right-hand side here. Beautiful data from, indeed, the Kepler mission and now tests ongoing. Also added to classical data, as Nick has explained in the introduction. Spectroscopy, that gives us the effective temperature of the star, and nowadays Gaia luminosities. Gaia is a beautiful satellite from the European Space Agency measuring the distances of stars, and if you know the distance and the brightness, you can work out the effective energy production. And so that's in addition to the beautiful seismic data that we get, right? So that gives us observed frequencies, and as it has been explained so beautifully again by Douglas and Jörn, we need to label each of the frequencies with its spherical harmonic. Else we can't do our job. And this is actually hard if you don't know what pattern to look at. Because for acoustic modes, we knew that very well from the sun. But if you don't know how the rotation changes patterns of these slow waves, well, then the mode identification, as we call it, is a challenge. And so that's why I work, in a certain sense, much slower than them. Because on the left-hand side, we do the modeling of the measured frequencies, but you do have to know which kind of spherical harmonic lies at the basis of the frequency. Now, how do we do that? We produce stellar models numerically these days by computer models. And if we admit, then we do not know very well how the rotation inside the stars work. We don't know if there is a magnetic field in the interior. Convective motions are a description that we tend to describe by an approximation. And we also have quite some mixing in massive stars. Why? Because the faster you rotate, the more you mix. You all know that from a cup of coffee with milk. That's a fluid. It's a different circumstance. But you do take a spoon to stir. You're bringing angular momentum to your coffee mixture. That's how I translate that, daily life. Else the coffee is cold by the time the milk is mixed. So we know fast rotation will likely bring more mixing, right? So in red, why in red? Because these are the phenomena that we're trying to understand and that we don't know very well, right? We then compute the oscillations from such a model by perturbing it gently, because the deviations are to a good extent linear, and then we predict the frequencies of particular modes and we compare them. Huh? So that's basically how we do our numerical work these days. Now, let's move to gravity modes, my favorite modes, in massive stars. And to show you that they actually do it, because I'm not telling you a fairy tale, I'm bringing one star and a plot from a PhD of one of my students, Jordan van Beek. The blue on top is a light curve that is measured by Kepler, and then overplotted in black is the frequency spectrum. Well, I should correct myself. It's actually the period spectrum, because we are now in the regime of slow waves, so the periods are higher. So we're looking for a pattern in the periods, as Jörn explained it. But in his case, the period spacing was constant of his slow rotators. You have seen that very well in his diagrams. Well, to guide your eye, because I'm assuming you're not an expert in gravity waves, in fast rotators, look at these red vertical curves. There is a pattern. It's not constant, as you see. As we go to higher periods, the lines come closer and closer together. This is a star at like thousands of parsecs away from us, where we see the Coriolis force in action in its core. I still find that amazing by the day. Why? Well, if I subtract this from this and this from this, etc., you get all these black dots in the lower curve. Huh? And these black dots, as said, they are not equally spaced. No, the more you go to longer periods, the less you are. Why is that? Well, this star has dipole modes with m equal to 1. In the explanation by Douglas, it's a dipole mode with prograde slow waves. What does prograde mean? It means that the waves travel along the rotation of the star. Yeah? And so if such a mode comes into your line of sight as observer, it comes a bit faster because you have the rotation and the wave on top of it is sort of surfing along. So you see it faster. Right? So the period of the mode goes down a little bit. And then, on the y-axis, we plot actually what we call the period spacing, that Jörn introduced. But so, the wave comes a bit faster compared to the case when there would be no rotation. And if you subtract two slightly smaller numbers, then the subtraction leads to a smaller number. So what does rotation do? It moves to lower periods and to shorter spacings. So you get a tilt in this diagram, and that's what's indicated in red. So by observing the stars with the space mission, and by carefully looking at patterns and understanding how the period spacing between the mode is tilted, we know the interior rotation of this star. Isn't that great? It took me 5 years to understand this, for which I apologize, but I had no sun to calibrate to. And not only me, we had many students looking at this at the same time. But now we understand it, and so once you do, then it becomes obvious. If you look at different stars, different B stars, and here are 7 plotted by, again, one of my students, Petr Papic. So the black is the data, and the red overplotted is the frequency spacing. The these all have prograde dipole modes. We managed to identify them. The upper one is a slow rotator. And then you shift and shift and shift to higher frequency, goes faster and faster in your line of sight, okay? So this is a fast rotator. Bit slower, slower, slower. And the upper one is a real slow rotator in the sense of having like a 100-day rotation, and this only a few days, okay? So by stacking these, well, we immediately derive the rotation frequency, and that's not the rotation frequency at the surface that you could observe by classical observation. No, that's the rotation frequency there inside the star where the modes are most sensitive. And this is close to the core. Yeah? So that's actually a very powerful tool that we have. And so assembling work done by many, many people in the community in terms of deducing the rotation frequency inside stars, massive stars, with gravity modes, we end up with a diagram that has, in this version, and it's 2001 to 21, sorry, it's already a little bit old. We have very many stars now where we have measured the internal rotation. And this is quite unique. There are no error bars here. That's not because I'm sloppy. That's because they are smaller than the symbol size. That's how precise Kepler data give us. So all these young, massive stars, they evolve into the stars that Jörn discussed, red giants, and they slow down tremendously. So anything below this dotted line was covered by Jörn, and we are here. Again, every single dot in this plot is hard work by many people. And most of them are very young people. And so now if we have these stars and we have gravity modes, and they also have acoustic modes, some do have that, then we can even deduce the rotation profile, as we call it. Not in a nearly as good as for the sun, as Douglas has shown, but near core rotation frequency and surface rotation frequency. And so we call that the level of differentiality. And so the triangle is the frequency near the surface, and the circle is near the core. And this was a big surprise, because we had expected in these more massive stars up there, well, we had expected that they would have a larger level of differentiality, but they don't, which means that there is a strong coupling between the convective core of these stars and the outer layers. And this was really not anticipated. Okay, so thanks to asteroseismology, we have been able to improve our models with a big factor, factor 10 to 100 in the inner workings of the rotation, let's say. And theoreticians in various groups, and you'll hear more about that in the afternoon, I guess from George, who is somewhere here, have been able to fix this. So that's a big achievement. Now let me move on. It also means that if we make models where we correctly describe rotation in the inner parts, we can work backwards and decide what the birth rotation of a star was. And this is a new plot made by one of my former students, now postdoc, Joey Mombach, where he has used these models to deduce the distribution of the inner rotation frequency of these stars. And you can see that in this sort of histogram. Now, these are field stars, about 500 in the galaxy, and we, of course, wonder, would that also be true when stars were born and are still in their cluster? And would it also be true for higher masses? So that's something that we are working on right now with lots of people, and we're moving to cluster asteroseismology. Why? Because then if stars get born together in a cluster, they must have the same age, they have the same initial chemical composition, and so they're equally old, so to speak. So we have more constraints, because we need more constraints to move to bring our models even into more troubles. I'm one of these persons who get very happy when models don't work, because then we can learn something, right? And here is an example by Dario Fritzewski, who has analyzed this new young open cluster to age date it, and this limitation is obtained by applying 3 different methods. One of them being asteroseismology in one star, and even adding one age measurement of one star tremendously reduces the uncertainty. This is a new field. I'm all excited about that. Here's another cluster where Gang Li did a similar technique, but here we have 11 pulsators in this cluster. These are cluster measurements by the TESS satellite. The TESS mission is operational right now, literally, you can take that. And so for gravity mode oscillations, we need long periods, and it has a continuous viewing zone, as we call it, where we can do this science. We are only beginning to do this, so there is a lot to be done, and here are all sorts of stars where to prove that I'm not telling you fairy tales, the red line here in frequency is the rotation frequency of the near core, and is very close to the oscillation frequency. So indeed, yeah, these are gravity modes in fast rotators. Then Gaia is there, and I think Joris de Ridder, who is one of my postdocs, is in the audience. He discovered 100,000 new non-radial pulsators in a Hertzsprung-Russell diagram. They are candidates, as I would call them. And so what I'm doing right now with Dan Hay, who is a postdoc in Hawaii, is check if Gaia can really deliver us a non-radial oscillation. It wasn't built at all to do that. But I tend to be a person who uses instruments far beyond their nominal use, just for the fun of it. And I can tell you in a, well, it's not yet published, but I'm sure we can convince the referee. 60,000 of these 100,000 are confirmed by tests. I find that amazing. And I have work to do, and it's so much fun. So I need lots of people to help me analyze it. Uksana, who is also in the audience, he will start complaining in the afternoon, saying, yeah, but all these massive stars have a companion and tidal forces, and you haven't discussed that yet. So, okay, that's true. I acknowledge that. And so tidal asteroseismology is yet to be developed, I would say. We understand some of it. And the one who is leading that right now, in terms of data, here's Luc Aspeert. He's one of my students. I just fixed his PhD defense as number 36 to graduate under my supervision. And that's amazing. He has 15,000 new eclipsing binaries from TESS, half of which oscillate. So I'm showing you that to say that going star by star, nah, I can't do that anymore. So we have to come up with some machine learning methods in this field. And I think my time is running out, but still beautiful tidal oscillations, I can't resist to show that, are happening. Yeah? So these are data where you phase fold across the orbit and you see all these wiggles. So the oscillations have a periodicity that is a multiple of the orbit. And so we know that from the Earth-Moon system, right? This happens. That's what tides do. And we have yet to learn how to exploit that. And the one who's doing that in my team is Zhao Guo, who is really very active in developing tidal asteroseismology. Anyway, I'm still assuming the stars are spheres, and this is not true. But nobody knows how to deal with asteroseismology in oblate spheroids. And so I have the immense privilege, together with 3 co-PIs, to work on this. I'm a little bit younger. I still have some time to work on problems. Yeah, yes, sorry. And so we're developing, or trying to develop methods to go to 3 spatial dimensions, where it all of a sudden matters how you look upon the star. Because if you have an oblate sphere and you look at the pole or at the equator, it doesn't give you the same result. But let me end with building the machine that is going to help us. This is Plato, to show you it's real. I am trying to convince you that I'm not giving fairy tales. This is a big machine that we are currently building, and that should get launched in 2026. But let me really end with my fountain of opportunities that I'm very proud of. Whether you work in astrophysics, in exoplanets, in galaxies, in massive stars, in clusters, or even in gravitational waves, because they have progenitors, asteroseismology is offering you a fountain of opportunities to improve your models for all these exciting phenomena in the universe. And so with that, let me also finally conclude and express my gratitude to the Crafoord Foundation, to the Academy for this really great, great honor, to my partner who is here and who has allowed that we raise our kids together in a 2 academic family, crazy, nerdy family, as our kids call it. And above all, to my more than 40 PhD students already by now, who have helped me to stay alive and kicking at a high pace with fast speed. And if it weren't for them, I would not nearly be as active as I am now. So thank you for all.